Okay.
Okay.
Question about that. Remi.
Okay, Michael, how you doing?
So could you go back to your share screen?
Okay, let's go back to share screen.
You know, it almost sounds like that vacuum fluctuation that reminds me of the surface charge on a battery, right? Where it's a very large number for voltage, but you can't actually use it.
Could you go to the page before where you showed the fluctuation? Like a little, like a sign. There you go.
This one? Yeah.
Next page then.
Yeah, you have to speak up, Michael. You're a bit distant from the microphone. You're coming across a little bit low.
Can you go down one page further?
One page further.
Yeah.
Yep.
A little farther. It's on that page.
Further. Yeah.
There. Stop.
Okay.
Okay. So this is your fluctuation, correct?
Yeah. So if you imagine.
Okay. So now this is maybe it's totally out there, but I had this job once where I was making occupancy sensors, where you walk into the room and the light turns on. And,
yeah.
And one of the big problems.
Close to your microphone again. Sorry, you come muffled. Yeah.
Yeah.
Okay.
Michael, have you changed your mic lately? Usually it's pretty clear. Today it does sound a little muddled and you're kind of fading out.
Oh, okay. Now I haven't changed anything.
Oh.
So what I'm suggesting is in alternating current theory, when you have what's called the 0-point crossing, okay, which is at the point in the middle, where it goes positive to negative at 0, that's where the current is maximum. Okay, and so what happens is when you switch your light on, you don't want it to be on the wrong point on the AC cycle. You follow? Or it creates heat. It creates resistance. So what I'm suggesting is, don't you want to look at that 0 point? You're saying it's a derivative, correct?
I don't really see what you're getting at. I think we're sort of talking at cross purposes. I mean, there's no current because there's no flow of charges. What we're talking about are the fields, yeah, the random fields and random fluctuations of the 0 point. Yeah, there's no particles. That's the point I'm making as well. You're dealing with 0 particle count. It's a fluctuation. It has 0 average, but it has a standard deviation. Can't really see what you're saying with the analogy, but I'm trying to think it through. Right. I do know what you mean about triangles.
So like you're thinking about the electric field and the magnetic field, how they're in 90 degrees out of phase. So when you hit the 0 here, there's another field.
I see what you're saying.
That's coming in and out of the page.
Yeah, I see what you're saying. So you're believing that I should be dealing with two fields. Yeah, so I should have an E field and a B field. That's what you're suggesting. Possibly. I mean, it's just a simple time model to give a ballpark. I'm just trying to find, this is where you get the B through from the creation operators. Yeah, I'll consider that. But if I remember, let me see. If I remember, the B field will be, is it C squared down on the magnitude of the E field?
You can also consider
I mean, if you take a plane wave, you'll have the E field equals C times B. So, what is it? Is that way around? Is it? I'll think about that one. I'll take that in and think about that. Yeah, but I'm sure it wouldn't be that difficult to put the magnetic field in. Yeah, I'll take that on board. Yeah, I'll take that on board. Thank you, Michael. I do agree. You've got a point there. Yeah.
I also have a quick thing to mention.
Okay.
Oh yeah, go for it, Michael.
Oh, Michael.
Oops, and he got me. There we go.
Yeah. So anyway, you also have to take into account that the measurements for vacuum in the presence of an atom, you have to take into account the vacuum energy of the self energy of the atom is basically a component of the vacuum energy present at the atom which is that's many orders of magnitude more than the vacuum energy that's present in completely empty space.
Yeah, that's, as I say, it's an initial paper. I do take on what you're saying, but I'm trying to deal with empty space.
Okay.
Yes, and yeah, but
Well,
I will take that one or two.
That's one of the reasons why in it, like the fine structure constant present in atoms predicts a much larger vacuum energy, because part of that vacuum energy is the particle itself at that point in space or at that location.
So you're talking about the self energy, the self energy that would result if you integrated down to zero. So the field,
So
the electron acting on itself.
So they were predicting a vacuum energy based on I believe it was spectral line splitting in atoms, and you can't predict, you can't ignore the energy, the mass energy or the self energy of the actual particle at that location when calculating the vacuum energy at that location.
So you're talking both the Lamb shift and you're talking about renormalization as well, aren't you?
I think so.
Yeah.
Something along those lines, yeah.
Yeah, the Lamb shift would be from the perturbation of the surrounding zeropoint field.
I think so.
The embarrassing problem in QED is the renormalization, is getting rid of infinities. Yeah. Yeah, I'll take that on board. I'll have a think about it. I'll say it's what they call an ansatz. It's the initial sort of when you put your workpiece on the tool, you know, on the anvil. So
you may be able to get away with a second order term or something that way.
Yeah, yeah.
Yeah. Well, Remi, thank you very much for sharing that with us. I sincerely appreciate it. And I feel guilty about pressuring you for the camera. That's just kind of been our policy. So, but
I've got the lighting strategically, so you can't see my stubble when you can't see the.
You look rugged with stubble. See, that's better than me. I just look homeless when I don't shave. You look rugged, so you have nothing to feel guilty about.
I'm going to switch it off now.
Okay.
Okay then.
Okay. Well, so why don't we do this? Let's everyone please put your hands together for Remi Cornwall. And that was a great presentation on ONSATs. And